Hey Finxters, what's up? It's Chris, founder of Finxter.com. Today from our living room, and in today's video I want to show you the Python set difference method. So this is part of the series about Python, the Python set methods, and understanding the Python set methods is, I think, critical for any great coder. So if you are a master coder, you for sure will understand and master all the set methods like set difference, union, symmetric difference, difference update, and so on. So there are many operations, and I will not only discuss the method, but also the runtime complexity of the method, and also some more advanced computer science concepts. So let's get started right away and learn about the set difference function method. So the set difference method is a method. So it is a method of the class, of the set class. So you can call it on any set object, and it creates and returns a new set. So it doesn't operate on an existing set. For this we have the set update, difference update method, but it operates on a new set. So it creates a new set and then calculates the set difference, which means that it takes the original elements of the set, and then it takes the set that you pass as an argument into the difference method. We will discuss this in a moment in an example, and it removes all elements from this new set that are in the set argument as well. So there are members of the set argument. So let's have a practical example, very simple example. So we create a set of 3 elements, like 1, 2, 3. We have another set like 1, 2, and now we call on set S we call difference, and we pass one set into the difference function, and we pass the set T, so we pass the set with 2 elements, 1 and 2, and we call it on this original set with 3 elements. So what is the result? The result is we take those 3 elements, we remove those 2 elements, and put all the remaining elements into a new set, right? So we get a new set with 1 element 3. And now let's check the original set S. It is unchanged. So the original set doesn't change. It returns a new set. So the set difference function returns a new set. And this is also the difference. So what happens if you basically run the same difference method, but with the update suffix? So we have difference update. It's another set method, and we pass the same set into it. Now this method doesn't create a new set. So you see there's no return value. So here when we called as difference, we got the return value of the new set with 1 element that is not like that is a set difference result. But here in this case we don't get any return value, but we operate on the original set. So if you print the original set, we get the return value 3, which is now the same as this example. But here you see previously the original set was unchanged. Now the original set S is changed. So if you want to modify an existing set, you would use the difference update method. Otherwise you would use the difference method. Good, so far so good. So I think these are already some important concepts, so that you know the difference of those 2 methods. Then, like, also one detail many coders actually don't know in Python is that you can pass multiple set into the set difference method. So maybe let's have an example. 1, 2, 3, 4, 5. So we have a set with 5 elements. We call difference on this set, so we can call it directly on the set object, and we pass now multiple sets into it, like 1, 2, another set with 2 elements, 3, 4, another set. No, let's add another set, 1, 2, 3, 4. Okay, so you see they are partially overlapping, those 2 sets, those 3 sets. So we have 1, 2, and here in this set we have 1, 2, 3, 4, and now we want to calculate the difference. Now let's maybe get rid of this 4th element. Now what is the result of this function method call? So you can pause the video, think about it. What would you expect to happen now? Yeah, basically it would remove so it would create a new set with all the elements from the original set first of all, and then it would remove all the elements in those sets you pass, right? So it would remove element 1, 2, 3, 4, and then it would try to remove 1, 2, 3, but it would see that 1, 2, 3 is already removed, so there's no point in removing it again. So the result is the set 5. It's the only element that was not part of any set argument. So you can pass an arbitrary number of arguments into the set difference function method. This is also a very important concept to understand. So I think now we only have one idea left that I wanted to discuss with you, and this is the runtime complexity of the set difference method. So say we have a set with n elements and a set argument with m elements. Yeah, so S would have n elements and this T would have m elements. Now the runtime complexity is, assuming n is larger than m, is O of n. Because we need to check for each element in the first set whether it is a member of the second set, right? So we have this membership check for each element in S. So for example, here in this case, we have check for 1 whether it is a member of T. Now we check for 2 whether it is a member of T. Now we check for 3 whether it is a member of T. And only for those elements that are not members of T, we would include them in the new set. So basically we have we go over all elements in the original set to check membership. Membership is O of 1. So membership has constant runtime complexity. It's pretty fast to perform membership on a set. So no matter how large the set is, it always takes the same amount of time. Theoretically, in practice it's a different thing, but theoretically it takes the same amount of time. And so we have overall runtime complexity of O of n, so we have linear runtime complexity. So let's maybe have a code example where we actually show this by example. It's always good to prove things by example, because the example is done in the real world, like with real Python code. It is not like a clean linear relationship between the size of the set and the runtime of the set difference method, but it's often like bursty and it doesn't work out that way in practice. Okay, so I have prepared something. So we use actually again we only need 2 libraries. Sorry, a library for plotting things and for tracking the time. And again, we create a set with different sizes from 10,000 elements. No, it's 100,000 elements. No, it's 10,000 elements to 5 million elements. So we have a lot of range of to 500,000. so from 10,000 to 500,000 elements. And so we have different sizes in the set. And we call the runtimes, we check the runtime. So we create 2 sets, S and T. As previously, we start the time and stop the time and append the difference of the time it took to compute once the set difference of those very large set. So basically here, what type of sets do we create? It doesn't really matter, but in this case we create a set of consecutive elements. So the set S has elements 0, 1, 2, 3, 4, 5 until the maximum number of elements is reached. And then we have the same set, but taking only every other element. Okay, so only for example, all even values in this case. So we have a step size of 2. Okay, so we calculate the difference, and now we track the time, and the larger the set becomes, the more time it should take, right? So let's check whether this is actually the case. We run the code, and it takes a moment to terminate the code, because it needs to perform the operations for 50 different very large sets, and then of course the memory will get cluttered, and it will perform it need to perform garbage collect and so on. So Python, it's kind of a heavy operation even for modern hardware. My computer is Intel Core i7 hardware, so it's pretty modern. Good. Okay, so here you see it's not a perfect straight line, but it approaches a straight line behavior, right? So we have linear runtime complexity. Here on the x-axis you see the set size, on the y-axis you see the runtime complexity, or the runtime in seconds, and you see for a set with 1 million elements it takes 0.05 seconds to perform this difference operation. Okay, so I think that's what we wanted to know. Now you also know the runtime complexity. You see it is quasi-linear. It has quasi-linear relationship between number of elements and the runtime. So actually the theoretical results turned out to be true on my computer for these smaller sets. Of course, if you would keep increasing the set size, you would obtain sets that are too large to fit in the memory of even my machine. So in this case, of course, the runtime complexity would explode. So it would exponentially explode and reach infinity soon. And because it would never stop at one point. So hardware is always limited. Hardware is never infinite. So the runtime complexity is not really in practice it's not linear forever, but for like sufficiently large elements, and theoretically it has a linear relationship. Okay, so so in future videos we will discuss future set methods. Thanks for watching this video, and see you in the next video. Bye.